You deploy a state-of-the-art autonomous coding agent into a massive, mature code base. You give it a standard prompt like fix the routing bug in the authentication module. Then you sit back and watch as the agent just spins for 20 minutes.
Oh, yeah. It runs endless bash commands, right?
Exactly. Recursively lists directories, reads the totally wrong configuration files, and just burns through this massive context window of input tokens. And all of this happens before it writes a single line of functional code.
Right.
If you work in machine learning or data science, you've likely watched your API costs skyrocket while an agent basically wanders the halls of your repository.
It is incredibly common. I mean, we are taking systems capable of highly deterministic, complex reasoning and dropping them into intricate architectures with nothing but an ephemeral, highly variable user prompt to guide them.
Yeah.
It's essentially the equivalent of asking a traversal algorithm to search a massive graph without providing the pre-computed index.
And that is exactly what we're unpacking today. Welcome to the deep dive.
Glad to be here.
We're looking at a 2026 paper by Lulla and colleagues titled On the Impact of Agents.md Files on the Efficiency of AI Coding Agents. The mission today is to rigorously examine the empirical data on how we actually initialize these models.
Yeah, we're looking at what happens when you stop relying on user prompts, right, and start using persistent version-controlled repository files to define the agent's search space.
Exactly. What's fascinating here is the paradigm shift from ad hoc prompting to, well, formal software configuration.
Right, because the research focuses on the agents.md file format, which has already been adopted in over 60,000 repositories.
That's 60,000, wow.
Yeah, it's essentially a machine-readable read-me specifically engineered for autonomous agents. Instead of a developer manually injecting coding conventions or build commands into a chat interface every single session, that structural context just lives permanently in the repository root.
Okay, but before we look at the raw efficiency gains, let's talk about what these files actually contain. Because, I mean, the authors didn't just scrape GitHub for any random repository that happened to have a file named agents.md, right?
Right. No, that would introduce a massive amount of noise. To maintain strict experimental control, they applied a filtering taxonomy.
Right, derived from prior work by Mohsenimofidi and colleagues, I think.
Exactly. They started with a known corpus of repositories utilizing these files and narrowed it down to those containing exactly one agents.md file located strictly at the root level.
Which eliminates the compounding variables of an agent trying to reconcile conflicting instruction files nested in, like different subdirectories.
Precisely. But the semantic filtering is where it gets highly relevant for practitioners. They needed to ensure these files actually contained actionable architectural data.
Not just boilerplate text.
Right. So they ran a local GPT-OS 120B model to classify the exact contents of the files, followed by manual verification. They only kept repositories where the agents.md explicitly defined things like project architecture, strict coding conventions, and structural best practices.
Basically isolating files that legitimately act as a bounding box for the agent's state space.
Exactly. And that rigorous filtering left them with 26 highly qualified production-grade repositories to evaluate.
Okay, wait. From an information theoretic standpoint, I have to push back a little. Why treat this as a distinct operational shift?
What do you mean?
Well, if a developer dynamically pastes those exact same architectural rules into a system prompt at runtime, the final tensor representations fed into the transformer's context window are theoretically identical to parsing an agents.md file.
Sure.
The model is processing the exact same token sequence.
Right. That is a very precise technical point. And yes, the token distribution inside the context window might look identical in a single isolated run,
Right.
but the distinction lies entirely in standardizing the deployment lifecycle. When you rely on dynamic session prompts, the initialization state is highly stochastic.
Because it depends on the human operator.
Exactly. A developer might forget to mention a specific linting rule on a Tuesday or fail to explain the database schema on a Thursday. By encoding this into an agents.md file, it becomes a version-controlled, collaboratively maintained artifact.
Oh, I see. It removes human variance from the context engineering loop entirely.
Right. It guarantees the agent evaluates the repository identically every single time it's triggered by a CI/CD pipeline.
So it's about eliminating the stochasticity of the initialization state. That makes total sense. Now, to actually measure the true computational resource delta created by that standardized state, the researchers had to build a sandbox.
Yes, a highly controlled experimental sandbox.
Right. They needed to isolate the agents.md file as the sole independent variable.
Yeah.
How do they ensure a clean environment?
The methodology is an excellent example of paired within task study design. From those 26 qualified repositories, they sampled 10 and then pulled up to 15 merged pull requests from each.
Okay, so that gives them a highly diverse data set of 124 real-world pull requests.
Right. And to evaluate the tasks, they utilized the GPT 5.2 Codex model.
Which is a solid choice, considering it natively supports repository-scale context and complex tool use, like Bash and Python execution. It perfectly mirrors the enterprise systems most practitioners are deploying right now.
Exactly. And here's how they handle the environment control. They utilized isolated Docker containers to perform a sort of code-based time travel.
Time travel.
Yeah, for every single one of those 124 pull requests, they checked out the repository at the exact commit state immediately prior to the merge.
Oh, I see.
And they extracted the specific historical version of the agents.md file that existed at that precise moment.
Meaning they aren't testing an old task against a newly updated instruction file. They are perfectly syncing the state.
Precisely. Then they executed the autonomous agent twice for each task. Run A executes with the root agents.md file perfectly intact.
And run B.
Run B executes with that file completely scrubbed from the file tree, leaving absolutely everything else unchanged.
Wow. And because each run happens inside a strictly isolated ephemeral Docker container, there's zero risk of state bleed, cached artifacts, or shared memory contaminating the evaluation.
Exactly. It's a very clean setup.
One thing that always bothers me about repository-level evaluations, though, especially when using historical GitHub data, is the input quality.
Oh, the issue ticket.
Yeah. Real-world GitHub issues are notoriously awful. You get titles like "Fix Login Bug with Zero Body Text."
Yeah, it's a mess.
So how do you accurately benchmark an agent's efficiency when the starting prompt is garbage? I feel like the variance in the model struggling to infer user intent would completely drown out the efficiency metrics of the AGENTS.md file.
That is a critical confounding variable in benchmarks like SWBench. To solve it, the researchers completely bypassed the original human-written issue tickets.
Oh, really? What did they use instead?
They fed the pre-merge file tree, and the actual pull request code diffs into their local 120 billion parameter model, the GPS 120B we mentioned earlier.
Yep.
They tasked that local model with synthesizing a uniform, highly detailed problem statement for every single task.
Oh, that is a smart workaround. It creates a perfectly standardized input format across the board.
Exactly. Every single run starts with a clear problem statement, explicitly defined expected behavior, and concrete acceptance criteria. They removed the inferring human intent step entirely.
So the only thing being tested is the agent's ability to navigate and modify the code base based on structural context.
Right.
Now, they also applied incredibly strict constraint parameters to the PRs themselves, right?
Weird, yeah.
The pull requests had to be strictly code-changing contributions. No documentation-only updates. And crucially, they limited the data set to a maximum of 100 lines of code additions and deletions combined, spanning a maximum of 5 modified files.
Yes, the constraint parameters were quite rigid.
Look, I have to challenge the bounds of that sandbox. By artificially capping the data set at sub-100 lines of code and a maximum of 5 files, aren't they fundamentally truncating the search space the agent has to navigate?
Wow.
Because if the true value of an agents.md file is providing architectural mapping, you'd expect that value to scale exponentially with repository complexity. By keeping the tasks this small, they might be drastically suppressing the maximum measurable impact of the context file.
That is a highly valid technical critique. And honestly, it's a limitation the authors explicitly acknowledge in the paper. By restricting the scope, they are intentionally bounding the search tree.
Right.
But if we connect this to the bigger picture of empirical evaluation, they had to impose these limits to establish a baseline.
Because of the variance.
Exactly. If they introduced massive tasks requiring the agent to modify, like 40 files across 12 directories, the stochastic routing decisions the agent makes during those complex refactorings could induce so much variance that it drowns out the foundational efficiency metrics.
So they needed a tractable, highly repeatable execution base to prove the core mechanism before scaling up the complexity.
Precisely. Establish the baseline on the micro before evaluating the macro.
Okay, let's look at that baseline data. The study defined operational efficiency through 2 primary metrics that directly impact a practitioner's workflow: token consumption and wall clock execution time.
Let's examine the token consumption first, as that maps directly to API inference costs. The introduction of the AGENTS.md file resulted in a statistically significant reduction in generation costs.
And they confirmed that using a Wilcoxon-signed rank test, right?
Yes, they did.
Mhm.
When the agent ran without the context file, the mean output token usage was roughly 5,744 tokens. But when the AGENTS.md file was present, that mean dropped to 4,591 tokens.
Wow, that is a reduction of over 1,100 tokens per task,
Right.
which translates to a 20.08% drop in mean output generation.
Right. And the median output tokens also dropped by roughly 16.58%.
What about input tokens?
The input token dynamics are interesting. Mean input tokens, including cached inputs, showed a modest decline of roughly 9.7 to 9.9%. However, the median input tokens remained statistically flat.
So the real story here isn't the input overhead, it's the massive reduction in the output generation required to complete the task.
Exactly, and that output reduction correlates directly with the wall clock execution metrics. This is where the data gets incredibly compelling.
Yeah, let's talk about the latency, the time it takes the agent to actually report task completion. The reductions are substantial.
They really are. The median completion time dropped from 98.57 seconds without the file, down to 70.34 seconds with the file.
That's a 28.64% reduction in median latency simply by having a static, standardized markdown file sitting in the repository root.
And to truly understand why that median dropped so heavily, we have to look at the variance. The researchers provided a violin plot visualizing these time-to-completion distributions, and the shape of those distributions is incredibly revealing.
Yeah, I'm looking at it now. If you look at the configuration lacking the agent.test.md file, the distribution is massively right-skewed.
Right.
You have a cluster of runs finishing under 200 seconds, but there's this visually striking, incredibly thick long tail that drags all the way out to the 1,000-second mark.
And that long tail is the visual representation of operational friction. It represents task instances where the autonomous agent essentially gets lost in the state space.
Just spinning its wheels.
Exactly. It initiates a read evil print loop, attempts to navigate the architecture, fails to find the right modules, and spends immense amounts of time and output tokens formulating iterative, exploratory bash commands just to figure out where it is.
But in stark contrast, the distribution for the runs that included the agent.test.md file has that massive long tail severely clipped.
It's a huge difference.
The data mass concentrates tightly around that lower 70-second median.
Because the context file acts as a strict bounding box. It prevents those catastrophic outlier events where the agent enters an unguided, unbounded generation loop.
Wait, looking at these token numbers again, there is a statistical discrepancy here that perfectly aligns with that violin plot.
What do you see?
Well, the reduction in the mean output tokens was about 20%, but the reduction in the median output tokens was only around 16.5%. In statistical distributions, when your mean shifts noticeably more than your median, it implies a significant change in the extremities of your dataset. So the agent.md file isn't just making every single run 16% faster in a linear fashion. It's actually acting as a truncation mechanism, specifically targeting those severe high-cost outlier runs. It cuts off the extreme edge cases.
That is exactly the mechanism at play. When the agent lacks the architectural map provided by the file, it occasionally falls into those highly inefficient exploratory states, burning thousands of output tokens just trying to formulate a valid approach to the code base. Suppressing those specific outlier events is what drags the mean down so aggressively.
But this raises a necessary validation question.
Okay, what is it?
If the agent is generating 20% fewer output tokens and finishing the task almost 30% faster, how do we know it isn't just failing faster?
Oh, that's a great point.
Are these efficiency gains happening because the agent is actually optimizing its workflow, or is it just writing shorter to generate code and terminating the run before the task is functionally complete?
It is a critical distinction. While the primary scope of this specific paper is measuring computational resource consumption rather than absolute functional correctness, the researchers did anticipate this exact confounder.
So they check the outputs.
Yes. To validate the integrity of the runs, they conducted a manual sanity check on a sample of 50 pull request tasks.
So they literally put human eyes on the actual code diffs the agent generated.
Exactly. They manually inspected the agent's final outputs against the ground truth human-merged pull requests.
To make sure it wasn't just like outputting blank files to save tokens.
Right. The objective was to confirm that the agent was consistently producing non-trivial functional code modifications that aligned with the intended task.
Which gives us confidence that the 28.6% median latency reduction represents a genuine operational optimization. But this leads directly into the question of the exact mechanism of action. We know the agent is writing functional code, but why is it doing it so much faster? Is the efficiency gained simply because the tighter architectural constraints force the model to generate a more concise final string of code? Or is the reduction in latency and output tokens a byproduct of the agent fundamentally skipping the exploratory navigation steps within the repository?
The paper strongly hypothesizes the latter. An agent doesn't just instantly draft code, right? It utilizes that read-evil-print loop.
Right.
It executes shell commands to list directories, uses tools like grep to search for variable definitions, and reads multiple files to infer the system architecture.
And every single one of those exploratory steps requires a round-trip API call.
Precisely. It generates output tokens to write the bash command, waits for the execution, and consumes input tokens to read the terminal output. So it's the cost of inference compounded by the latency of network calls and environment execution.
So by providing the architecture, the project structure, and the coding conventions up front in the AGENTS.md file, you effectively bypass those initial planning iterations.
Exactly. The agent is handed the pre-computed index. It can immediately target its edits, write directly to the relevant files, and initiate the code modification. The massive reduction in latency and token generation is primarily derived from eliminating that exploratory overhead.
That makes perfect sense. The model doesn't need to spend 500 tokens asking the terminal how the repository is structured if the markdown file tells it on initialization.
Right.
Now, the researchers also outlined a roadmap for future work based on these findings, didn't they? Because treating the context file as a simple binary, just present or absent, is only the first step.
Yes, the immediate next phase of this research is evaluating how the structural specificity and semantic organization of these files impact outcomes.
Like, what if an agents.md file is poorly organized?
Exactly. If it's outdated or contains hallucinated build commands, does it induce negative efficiency? Does bad context confuse the agent more than no context at all?
That's a huge question for enterprise deployment.
And furthermore, future work will integrate rigorous semantic correctness checks, moving beyond manual sanity checks to compare agent outputs against the original human-merged PRs.
Integrating structural similarity analyses to map exactly how the constraints in the configuration file shape the logical flow of the generated code.
Exactly.
So let's synthesize the core insights for the practitioners listening. The study by Lulla et al. Provides rigorous, paired empirical evidence that persistent repository-level context files fundamentally optimize the operational deployment of AI coding agents.
Specifically the AGENTS.md format.
Right. By supplying upfront architectural and structural parameters, these artifacts effectively truncate the agent's search space. They act as a bounding box that clips the long tail of computational latency.
Right, yielding that roughly 28.6% median reduction in wall clock execution time.
And a 16.5% median reduction in output token generation for targeted tasks using GPT 5.2 Codex.
And if we project these findings forward, I want to leave you with a final concept regarding the architecture of these systems.
Okay, what is it?
If the presence of static, human-curated repository context drastically minimizes the execution costs and search space for autonomous agents, how long will it be until that curation process is entirely automated?
Oh, wow.
We already rely on static analysis tools to map code-based topologies. We may be rapidly approaching a paradigm where CI/CD pipelines automatically compile, synthesize, and update these agents.md artifacts in real time on every single commit.
So the system dynamically maps its own constraint.
Exactly. It would generate the exact initialization parameters the AI agents need, entirely removing human developers from the context engineering loop. We're looking at a future where the codebase autonomously writes its own instruction manual on how it should be modified.